All right, so let us do some example problems for conservation of energy. First of all, let's remember what the conservation of energy equation says. It says that the initial kinetic energy plus the initial potential energy of the system must be constant. So that means it's the same as the final kinetic energy plus the final potential energy of that system. Now, as I said in the previous lecture, initial and final are just labels. It doesn't have to be the initial state and the final state. It could be state 1 and state 2, somewhere in the middle. It doesn't matter where you're measuring. The total energy is always the same no matter where you measure. But in general, when we write it as initial and final. And then remember, potential energy stands for two different potential energies, gravitational and spring. And of course, as you go further into physics, you learn that there are more potential energies, like electric potential energy and things like that. But for now, we're just doing gravitational and spring. So let's do an example. Let's take this situation. We have a hill that has a funny shape like this. And there's a block at the top of the hill. And let's say that the top of the hill is 20 meters high. The hill goes all the way down to the ground level, and then it rises back up to a height of 5 meters above the ground. And then we're going to say, let this location be location A, and this location be location B. And of course the question says, how fast will the block be moving at A and at B? Okay, so this is very similar to the examples we've done before, except there are two different locations we're looking at. Not just, the initial state and the final state. There's actually the initial state, then there's state A and state B. Okay, but we're not going to worry about it. Let's worry about state A first. So we want to know what's the velocity when the block reaches point A. Well, as before, we have the equation kinetic initial plus potential initial is kinetic final plus potential final. Now for this, what's our initial state? Well, the initial state, of course, is at the top of the hill. And what's our final state? Final state is at location A. Now we ask our questions. For the initial state, are we moving? Well, the block's at the top of the hill. We haven't started sliding yet, so no. Kinetic energy initial is 0. We're not moving yet. Potential. Are we some height above the ground? Yes, we're 20 meters up, so there's some MGH. Initial state. Is there some spring involved? No, no spring, so that's just 0. Now we go to the final state. Our block slides down the hill. We're now at point A. At this point, are we moving? I assume we are. I have no reason to doubt. We've slid down the hill, so obviously we started moving. I don't see any reason to think we've stopped, so I assume we're moving 1/2 mv squared. Are we some height above the ground? Well, no. At point A, we've fallen all the way to the bottom, so no height. And is there any spring involved at point A? No, there's no spring in this problem, so that's always going to be 0. All right, so there we go. There's our equation. Let's look. There's an m on every single term, so we could cancel out the m's. And what's left over, we have 9.8 times the height at location initial, that's 20, equals 1/2 v squared. So v is the square root of 2 times 9.8 times 20. Get out your calculator, and you write 2 times 9.8 times 20 square root, and we get 19.8. All right, good. So we now know the velocity of the block when it reaches location A. Now we want to go to location B. So again, we think about what is the initial and final state for this. Now here we have a choice. First of all, the final state, of course, is location B. That's easy. But what about the initial state? What do we take as our initial state? Well, as I said, we have a choice. Either we take the very beginning of the problem, when the block is at the top of the hill, that's our initial state. Or we could say location A is the initial state. Both will work. Either way will work. You're allowed to choose either one. What I'm going to do is I'm going to choose the beginning of the problem, the top of the hill, as our initial state. And the reason is because, just as has happened in the past, I'm always reluctant to use information that I had to calculate to solve a problem, because if I calculated that information wrong, then the rest of my calculations will be wrong too. So if I use location A as my initial position, then I'm going to have to inevitably use this 19.8 that I just calculated as his initial velocity. But, you know, maybe I calculated that wrong. Maybe I stuck it in my calculator incorrectly. So since I have a choice, why not just use the same initial state? I was at the top of the hill. Who cares about what happens in the middle? I end up at location B. So that's what I'm going to do. So, same equation. Oops, let me use blue. Kinetic initial plus potential initial is kinetic final plus potential final. So again, same questions. Initial state, we're at the top of the hill. We haven't started sliding down yet. We're waiting to go. Are we moving yet? No. No velocity. Are we some height above the ground? Yes, we're 20 meters above the ground, so there's an MGH. Is there a spring? No spring. Final position. We've slid down the hill, reached location A, then slid back up to location B. At this point, are we moving? Well, I assume we're moving, and in fact, the only way we would not be moving is if location B was higher than the initial location. But since location B is only 5 meters up, and our initial location was 20, then I can assume we're still moving. So, 1/2 mv squared. Second question, are we some height above the ground? Yes, we are. We're 5 meters above the ground, so there's some MGH final here. And spring, there's no spring, so that's 0. And here's our equation for this step. Now let's look, is there anything that could cancel out? Remember, the only time something can cancel out is if every single term has it. Not just 2, not just 1, but all of them. So let's look. There's an M on the first MGH, there's an M on MV squared, there's an M on MGH final. Yep, so there's an M on every term. All the M's will cancel out. The G, I cannot cancel the G, even though there's a G here, there's a G here, but because there's no G here, there's not a G on every term, so I cannot cancel it. So I have to keep it, but that's okay. 9.8 times the initial height of 20 equals 1/2 v squared plus 9.8 times the final height, which is 5. So there's our equation. Again, I want to solve this for v. So what do? Let's see, 9.8 times 20, that's 196. equals 1/2 v squared plus 5 times 9.8. That's 49. So v is going to be the square root of, let's see, 196 minus 49. So I brought the 49 over. And now 1/2 v squared is on the right, so multiply by 2 to get it over to the other side, and then I take the square root. So that's what I do. 196 minus 49 times 2, square root it. And here I get 17.15. Now, does this make sense? Does this answer for part B actually make sense, or can I tell if it's wrong? Well, let's use a little intuition. Remember, every time you're solving a physics problem, you should always keep in mind the intuition about the problem. You know how the world works. You have a way of thinking about things, and you can answer some questions. So my question to you is, do you think when the block slides down to A and then it slides up the hill to B, should the velocity at B be greater than the velocity at A, less than the velocity of A, or about the same? Well, if you think about it, think about an object moving along the ground. It's rolling. Let's say you roll the ball along the ground, so it's at A, and then it goes up a hill. As it tries to go up the hill, will it slow down or will it speed up? Obviously, it's going to slow down as it tries to go up the hill. So my assumption would be the velocity at B should be less than the velocity at A. And is that true? Well, look here. The velocity at A was 19.8, so about 20. The velocity at B is only 17. It is less than, so it makes sense. If I would have gotten something like 27 at B, then I could have said, something's wrong here, it's not making sense, let me go back and make sure I did my math correctly. You should always remember that these are supposed to be real-world problems. Don't just go through solving these problems and not thinking. When you get an answer, see if you can tell if it makes sense. Sometimes you can't, but sometimes you can. And in this case, you have the ability to ask yourself, the fact that B was a different number than A, should it be less than? And so you say, well, let's see. It slid down, so I would imagine the fastest it's going to go is when it's at A, because that's when it's at the lowest point. Then as it tries to slide up the hill, it must lose speed. So I would assume B is going to be less than A, and in fact A should be the fastest speed of all of them. Now, let me go ahead and solve this again, only this time I'm going to solve it going from A to B. So notice here, I solved the problem going from the initial state to B, skipping over A. Well, now I want to do the problem, only now I'm going from A to B. So let's remember what it looked like. So here's B, here's A, here was our block, from here to here was 20, here to here was 5, and I found in this part A that the velocity here was 19.8. So let's solve part B again, only this time instead of starting for our initial position at the top of the hill, I'm going to say A is the initial, B is the final. Will anything change? Let's see. Kinetic initial plus potential initial is kinetic final plus potential final. All right, so initial state, we're at location A. What is location A again? Well, I've slid down the hill. I'm now sliding at A, and I'm on the ground. So at that point, am I moving? Yes, of course I'm moving. I know what my velocity is, so 1/2 mv squared. Second question, am I some distance above the ground? No, I'm at ground level, so mgh is 0. And of course there's no spring. Now, final location, I've now slid back up to point B. At that point, am I moving? Well, I assume I am. I have no reason to doubt. I mean, one thing to note is location B is above location A. That is true. But because at location A I already had a velocity, it's possible that I'm still moving. If at location A I started with no velocity, then there's no way I could possibly go higher. But the fact that A had a velocity, I assume I can still be moving. And it's a safe assumption, so we'll have MV final squared. Am I some distance above the ground? Yeah, 5 meters, so MGH. And no spring. So now this is what my equation looks like. Anything to cancel? Well, there's a 1/2, MGH doesn't have 1/2, so I cannot cancel the 1/2. M. There's an M on every term, so the M's will cancel. Good. There's a V and a V, but those are two different V's. One's V initial and one's V final, so I can't cancel them. So that's it. I can't cancel anything else. That's fine. Let's just stick our numbers in. 1/2. The velocity at A was 19.8 squared equals 1/2 V squared, which is what I'm looking for, plus 9.8 times 5. All right, so now we get our calculator out. 19.8 squared divided by 2. That gives us 196.02 equals 1/2 V squared plus 49. So bring the 49 over. 196.02 minus 49 equals 1/2 V squared. 196.02 minus 49 gives me 147.02 equals 1/2 V squared. Multiply by 2. I get V is equal to the square root of 2 times 147.02. So 2 times 147.02 square rooted, I get 17.15. Now my hope is that this is the same answer I had before. Because again, I get to choose what my initial and final positions are. It doesn't matter. Of course, the final should be B because that's what I'm looking for. But the initial state, it doesn't matter where I choose. So the fact that I chose a different initial state should not change my final answer. So what did we get? 17.15 here, 17.15 here. Perfect. They match. And this shows whether I do it from the initial state at the top to B or somewhere in the middle to B, it doesn't matter. As long as you fill in the information correctly, the answer will come out to be the same. All right, so that's that example. Let's try another example. Let's try to find one that's really, really complicated. How about this? How about we have a hill and then a spring wall. There's a block at the top of the hill whose mass is 10 kilograms. The spring has a spring constant of 200. And the height of this hill is 5 meters initially. For this situation, the block's going to slide down the hill, reaches the bottom, hits the spring, and it's going to compress the spring. The question is, how much will the spring compress? So the maximum compression. When a block hits the spring, it's going to push it in. How far will it push it? All right, well, of course, kinetic initial plus potential initial is kinetic final plus potential final. All right, let's do our normal thing. What's our initial state? We're at the top of the hill. Final state, we've hit the spring, compressed it as far as it'll go. Okay, so initial state. Are we moving yet? No, I'm at the top of the hill, I'm not moving, so no kinetic. Am I some distance above the ground? Yes, 5 meters. Okay, so MGH. Third question, at the initial location, is there some spring involved? No, I'm not hitting a spring, I'm not compressing or stretching or anything. There's no spring there. All right, initial is done. Now the final location. I've slid down the hill, ran into the spring, and pushed the spring as far as it'll go. At this point, am I moving? Well, no, I assume I'm not moving. And it must be that I'm not moving, because if I'm still moving, then I'm still compressing the spring. So if I've compressed it as far as it's going to compress, I must have stopped. Thus, no kinetic energy. I've stopped. Second, am I some distance above the ground? No, I'm at the bottom. I've already slid down to the bottom, hit the spring, compressed it. So I'm no height above the ground, no MGH. Third question, am I compressing or stretching a spring? Yes. At the final location, I've compressed a spring, so there's 1/2 kx squared. All right, so here's my equation. Now all I have to do is plug my numbers in. Is there anything I could cancel? No, there's nothing that's the same for both terms, so I just have to stick everything in. The mass of the block, 10 kilograms, 9.8. The height, 5 meters above the ground. The other side, 1/2 k, spring constant is 200, x squared, where x is how far the spring compresses. So x is the thing I'm looking for here, the distance the spring is compressed. All right, so we're going to solve this for x. X is going to be equal to the square root of, all right, we've got 10 times 9.8 times 5. And then I need to, 1/2 of 200 is 100, so I bring the 100 over, divide by 100. And then I take the square root of both sides to get rid of the square. And what do I get? 10 times 9.8 times 5 over 100, square root of this. I get 2.21 meters. So how far will I push this spring in? 2.2 meters. And there we go. So here we have a system that has both gravitational potential energy and spring potential energy in it. But no big deal. We just asked the 3 questions we always ask for our initial state and then for our final state. That tells us which terms are important. Once we know which terms are important, we just plug the data in, and it's a matter of solving for the unknown. So let me do one more, just to show that there can be different types of stories. So far, almost everything has been you slide down a hill or up a hill or something. Well, let me do one with a different story. Let's say you have a spring-loaded gun. A spring-loaded gun has a spring constant of 500 newtons per meter. A 1-gram bullet is placed in the chamber. You cock the gun, compressing the spring by 0.5 meters, what will be the bullet's velocity? Okay, so obviously a different sounding story, but you're going to see we're going to solve this the same way. Let's draw a little picture just so we get an idea. Here's my gun. Here's a little spring and our bullet. And so we cock the gun. Let's say this is a really big gun because it's cocked by 0.5 meters. That's a real big spring. So you compress the spring and the bullet's sitting in there, waiting to be released. You pull the trigger, that shoots the bullet out, and you want to know how fast will it be moving when it gets shot. So the initial state, of course, the bullet's sitting in there, the spring is loaded. Final state, the bullet has left the gun. All right, so what's our equation? Kinetic initial plus potential initial is kinetic final plus potential final. All right, initial state. What's the initial state? The bullet is loaded into the gun, we've compressed the spring, and we're waiting to release it. At that point, are we moving? Is the bullet moving? No, the bullet's not moving, it's waiting to be released. Are we some distance above the ground? That's not important here. When the bullet is shot, it leaves the gun at the same height as it starts. I'm not told that the gun is some distance above the ground, so there's no MGH in this problem. It's all about the spring, so no height. Is a spring being compressed or stretched at location initial? Yes. So 1/2 kx squared. Now we go to the final position. Final position is we've shot the gun, spring gets released, pushes the bullet out of the gun. At this location, are we moving? Yep, we are, so there's 1/2 mv squared. No height, because we left the gun at the same height as we started. There's no difference in height there. And in the final position, is a spring being compressed or stretched? No. We've already released this spring. The spring has pushed our bullet out, so there's nothing to do with the spring anymore. He's done. So no spring. Perfect. So let's look. Are there anything that's the same on every single term that we could cancel? Yeah, the 1/2. There's a 1/2 here and here. But that's it. Nothing else can be canceled. So I've got kx squared equals mv squared. All right, k. What was our k? K is right here. We have 500 times x squared. X, remember, is how much the spring is compressed. In this case, it's 0.5 squared equals the mass of the bullet. Mass of the bullet is right here. It says 1 gram. Grams are bad. We want kilograms. So what is 1 gram in kilograms? Well, it's 0.001. Right, 1 over 1,000. Because a kilogram is 1,000 grams. So if we only have 1 gram, that's 1/1000th. So 0.001 times v squared, where v is what I'm looking for. All right, so v is going to be 500 times 0.5 squared. I got to divide over the 0.001, and I have to take the square root to get rid of the square. Right, so 500 times 0.5 squared divided by 0.001, and I take the square root, and I get 353.6. And there we go. I now know the muzzle velocity, or the bullet's velocity. How fast will a bullet be moving after it's shot out of this gun? 353 meters per second. So there we go. Here we have a problem, sort of a different story. You know, it doesn't look like the sliding down a hill or sliding up a hill type thing, but it's still conservation of energy. You have a system in one state, you release it, it does what it does, you now look at its last state. And you say the energy must be constant, the energy doesn't change, so we do conservation of energy. And that's all there is to these types of problems. There's a whole bunch of different variety I can give. I've showed a good number of examples, and I hope you see by now that every time I solve one of these problems, I do it exactly the same way. And in my opinion, you should be solving them that way as well, because it kind of takes all the thought and questions out of play. You're just basically cranking out what the equation must be. Which terms do you need? Which terms are zero? You're not really thinking about it. You're just saying, for this state, am I moving? If yes, I put this. If no, I put that. And so on. So I hope you practice a bunch of problems. You should see a bunch of practice problems on Canvas. So definitely practice them. Future lecture, we may talk about how to incorporate work. So maybe there could be friction involved. Or what if there's an extra force? So far things just evolve naturally. But what if there are outside forces acting on the system? Friction is one of them. You know, if you slide down a hill, that's fine, but what if the hill is made of grass? Obviously, as the block slides down a hill, if the hill is made of grass, it won't necessarily speed up. It might slow down. The grass may slow it down. So that seems to violate conservation of energy if we don't take friction and things like friction into account. And so we're going to modify conservation of energy in a very simple way to allow for things like friction so that more real-world problems can exist. But for now, know how to do the straight-up normal conservation of energy, and you should be good. So, until next time.